This presentation is actually entitled what you see here. We're not looking for the optimum magnetic loop because there is no optimum magnetic loop. That depends on your needs. What we're looking at is the optimized magnetic loop. And what that means is the one that's getting your loop to work the best it possibly can, not so much not so much being in the optimum loop because there are all sorts of loops, but optimized magnetic loop. Here we see a bunch of magnetic loops. These are just pictures I took off the internet, including mostly homebrew magnetic loops, except for the top three up there, which are commercial versions of the loop, with the probably the best known one, the MFJ loop. I don't know what state MFJ is in these days, but that's the MFJ loop, and a couple of other commercial loops. The rest of them are homebrew loops of various forms and sizes that you can see, shapes and materials and so forth. And the magnetic loop is certainly a very popular homebrew and also commercial loop in the ham radio world, and quite popular because of its unique properties, being very small, and yet the fact that it rivals large antennas. So it's handy for people with limited spaces or who like to go traveling and so forth. However, despite the fact that it's very popular, if you go on the internet, you're going to find that there really are very, very few optimized designs, meaning very few designs that are really getting the best performance out of the loop that they're showing you or selling to you. And there are very many misleading ads. If you read the glossy ads that are published in the magazines or even on the internet, there are many misleading ones that tell you this is the greatest loop ever built. Well, I look at many of those and I say it is not the greatest loop ever built. It's got many unoptimized characteristics about it that if some changes were made in it, it would work a great deal better. And when you go on these websites, not many of them tell you sound principles on how to optimize a loop, how to make it give you the best performance, or if you're building one, how to build it so that it will produce the best results. That's what we're going to talk about here today. If you ask the average ham about antennas and you use the word optimize, about all they think about is this red worm here, or this red demon here, SWR. To them, that's all optimized means. If I get a low SWR, I've got an optimized antenna. Well, and maybe perhaps for some antennas, that's about all optimized means. But that's not true for the magnetic loop. Far from it. So don't think that SWR is the only thing that you need to get right to get the magnetic loop right. Now, maybe if you're running a simple dipole like this one, here's a self-supporting portable dipole. Maybe for a simple dipole, SWR is about the only thing you need to optimize. So optimization is sort of a one-step procedure for a simple dipole. We just use the classical formula that the length in feet is the frequency divided by 468. Most hams who've been around a little while know this formula, and that's probably about the only thing you need to do to a simple dipole, but it's by no means the only thing you need to do to a magnetic loop to optimize it, to get the most of the amount of your transmitter power to go out as radio waves. In fact, there are 7 things you need to do to a magnetic loop, including for both transmitting and receive, if you want it to do the best job it possibly can, which is what I mean by optimizing. You need to get the conductor diameter the correct in comparison to the size of the loop. You need to build it out of the right materials. You may think you know what the right materials are. And I think you're going to get a few surprises in the presentation today, at least some of you will. How about the shape of the loop? Well, you may think you know what the shape of the loop is. You may think the word loop tells you what the shape is. No, it doesn't. You may never have heard of the term self-resonance. That's why I put the 3 question marks on it. Self-resonance, it has a lot to do with optimizing the magnetic loop. Matching method. How do you match the loop correctly? How about the tuning method? What's the best method to tune this loop? I think most of you have some ideas about tuning a loop. What's the optimum way to do it? And that optimum may be to save some money. And then suppose you're using the loop only for receive purposes. There are some considerations when you're going to make a magnetic loop for receive only purposes. And there's many good reasons why you might do that. So it isn't just one thing that you need to do to a magnetic loop to make it optimized. There are 7 things you need to be sure are present. And this is not only true for one you may build, it's also true to one you're thinking about buying. If the loop you're thinking about buying doesn't cut the mustard in all 7 ways, don't buy it. Okay, so what's this presentation about? How magnetic loops work? No, I'm not going to talk about how they work. There's plenty of stuff on the web about how they work. I'm going to, are we going to talk about the pros and cons of magnetic loop? I think most of you know that magnetic loops are great little antennas, and they compete very well with antennas much bigger than they are. Am I going to tell you how to build them? No, I think how to build them is pretty much known in the ham community. What we are going to talk about, though, is how to maximize their performance. And that's the factors, those 7 factors that I just put up on the screen. That's what we're going to talk about, optimizing those factors. If you get them all maximized or most optimized, you're going to have a magnetic loop that's really going to do its job. And believe me, very few magnetic loops designs that you see on the internet, and even quite a few of the commercial loops, are not optimized. All right, let's begin with the biggie. To me, the number one, the one, as Dave Karcher says at Wendy's. Here's the biggie. The one, if you want to get right, get this one right. If you forget the other 6, you won't be in much trouble. But if you forget this one, you're going to shoot yourself in the foot every time. And it is the relative size of the conductor compared to the size of the loop. This is going to determine 2 things for you. The efficiency of the loop. And what's efficiency? Well, how much of your energy goes into radio waves compared to how much of your power from your transmitter gets lost as heat. And it's going to determine what the lowest frequency this loop will operate on. These are the 2 things, and this is the biggie efficiency factor. So we deal with it first. Okay. Let me make it very clear to you. Once we understand this little graph here, I don't think you'll ever doubt how important, how big the conductor is, how big the material the loop is made out of compared to how big the loop is, because it is the number one important factor for optimizing. Let's take a 4-foot square loop, as that's what it says across the top, a 4-foot square loop. You'll learn later why I use a square loop here. It's pretty much the same for a round loop or an octagonal loop or even a triangular loop or whatever shape you make the loop. I use a 4-foot square loop because I think square is the best shape, by the way. I think it is the optimized shape for a loop, for a magnetic loop, and we'll get to that at one of the points. But let's use a graph for a 4-foot square loop. It's going to be very similar for other shapes of loop. Let's make this loop here, as they see in 3 curves, out of 3 different materials. In other words, the size of the conductor is of different ratio compared to the size of the loop itself. We're going to make it out of number 10 wire, which is pretty good size wire. We're going to make it out of a piece of coax, RG8. You'll see a lot of designs on the internet where they make the loop out of coax, RG8 coax, for example. See a lot of internet designs making mag loops out of RG8 coax. Or we're going to make it out of 2-inch conductor, 2-inch pipe maybe, or various other things that are 2 inches in diameter. Let's look at the efficiency of these three different states. All three of these are 4-foot square loops, could be round loops. A round loop would have very similar curves to this. On the left, we see the efficiency from nothing, none of the power we put into it gets out, to all of the power that we put into the loop gets out as radio waves on the left. And at the bottom, we see megahertz, the various bands that we have. And I will show it to you both in bands and in frequency here. Notice that number 10 wire falls below 50% efficiency, which I've just said is arbitrary. There's no standard for how efficient the loop is. I mean, hams work with antennas that have various efficiencies, from very efficient to very inefficient. Any of you use a rubber ducky? That's a very inefficient antenna. We make lots of contacts on a rubber ducky, but it's not very efficient. So 50% is just arbitrary here to illustrate this point. But 50% is probably a pretty good arbitrary point to set. So everything below the line is less than 50% efficient. Everything above the orange area is over 50% efficient. Okay, if we make our 4-foot square magnetic loop out of number 10 wire, just a wire loop, 4-foot square, it isn't any good below 15 meters. If we make it out of coax, out of common 4/10 inch diameter, roughly ½ inch diameter RG8, it isn't any good below 20 meters. Its efficiency has fallen below 50% by the time we get to 20 meters. We get to 40 meters, its efficiency is way down at about 5%. And we get down to 80 meters, its efficiency is down about 2%. Now let's take a look at a mag loop made out of 2-inch diameter pipe, which is a fairly good size. The ratio of 4 feet in diameter for the loop and 2 inches in diameter is much better. As you can see, it's pretty efficient down to about 40 meters. At 80 meters, it's still fallen off pretty badly. So you can see how important the diameter of the conductor compared to the size of the loop is. So if you see a commercial loop that's got weeny conductors, don't buy it. It's a bad loop. I don't care how glossy the ad is in the magazine. This should make the point for you about this number one point, the conductor ratio to diameter to the loop size. So here's a takeaway image that I want you to take away right from the beginning. Scratch this picture in your memory. Get it embedded into your mind as an image. The next image you're about to see. This is an optimized square loop, 4 feet in diameter. Here it is. Here's a 4-foot square magnetic loop. We'll talk about what it's made out of later on here. It's one of my loops. It's 4 feet on a side. And notice the ratio of the diameter of the pipe compared to the size of the loop. It's roughly about 24:1. This is the relative loop to conductor diameter ratio. If you see a magnetic loop, or if you're thinking about building a magnetic loop, and the ratio is bigger than that, in other words, 50:1 or 100:1, it's going to be a bad loop. Don't do it. If the loop you're going to build or you're going to buy has a ratio that's higher than 24:1, don't buy it, don't build it. About the only commercial loop I've seen that's available today that gets down to anything decent to 40 meters is this Ciro Maggioni Italian MIDI magnetic loop antenna. It's efficient down to 40 meters because, as you can see, the conductor is big. It's big. So this is an efficient loop. It's pretty expensive, but it's a good loop. It's 6.5 feet in diameter, and it has 3-inch conductors. It meets my criterion for an efficient loop down to 40 meters. But below 40 meters, it doesn't work very well. I mean, lower in frequency. It's not efficient at 80 meters. All right, that takes care of the biggie. If you don't optimize the rest of them, but you optimize that number one, you're still going to have a pretty good loop. Number two, the material that you build the loop out of. Now, I like this one because it's going to save you dollars or pounds or yen or euros, depending upon. I give this lecture all over the world by Zoom. I've lectured in New Zealand and Australia and South Africa and in Europe too as well. So all of these, that's why I've got all these different currencies. But wherever you live, you're going to save money with this factor. So this is monetary optimization. Magnetic loops, like many other antennas, all are affected by skin effect. All antennas are affected by skin effect. What's skin effect? Well, most of you probably have some idea what skin effect is. When you put alternating current, especially RF, which is just high frequency alternating current, down a conductor, it all rushes to the surface. The magnetic field that's in the conductor causes the alternating current to immediately seek out the surface and the edges, the outer edges of the conductor. As a result, there's no current inside the middle of the conductor. Here that's symbolized by this drawing on the left. I've symbolized it with a piece of aluminum wire. Why aluminum? Well, that's what we make most of our antennas out of. It could be copper or brass or steel or stainless steel. Same effect, it takes place. But I'm just showing it here as aluminum wire just for reference. You notice that the current, which symbolized here in red, is all on the surface. The inside of that wire doesn't even have to be there. It could be total vacuum, and this piece of conductor would work as well. It could be a sleeve, a cylinder, and it will work just as well. Skin effect is very meaningful in making antennas because all the activity is on the surface. Notice how thin that skin is. I'm showing it to you here in copper and in aluminum. Notice how thin the skin is. On 80 meters, for example, in copper, it's 4.2 mils. What's a mil? A thousandth of an inch. It's only 4 thousandths of an inch thick on copper. In aluminum, it's a little thicker, about 5.1 thousandth, but it's only thousandths of an inch. Look at it down at 440 or 70 centimeters. It's only 3/10,000ths of an inch thick in copper and 6/10,000ths of an inch thick at 440. That's a teeny, teeny, teeny tiny skin on the surface. Solid metal is not required to make magnetic loops. Foil on PVC pipe works just as well as solid copper, or at least copper pipe. So all the gurus on the magnetic loop websites that are just absolutely sure that you got to make magnetic loops out of copper pipe are barking up a hollow log. You can make perfect magnetic loops out of PVC pipe covered with sticky aluminum foil tape that you can buy down at your hardware store. But when you buy the tape, at least buy it thick enough. Be sure it's at least thick enough to use on the various bands you're going to use it on. Here to me is the optimized material to build magnetic loops out of. Yes, it's just PVC pipe, and you cover it up with what's called high vac, heating and air conditioning and venting, aluminum foil tape, which you can buy at any hardware store or you can get on Amazon off the internet in all sorts of widths, from 1/4 inch up to 4 inches wide, very easily. And you can glue it together, miter cut the corners and glue it together and then cover it with aluminum foil tape. And it works just as well as if it was made of solid copper rod. Why build it out of copper and spend a total bunch of money on it when you don't have to? Buy this stuff. Aluminum air conditioning, or what's called HIVAC, heating air conditioning. That's what HIVAC stands for. AC duct tape. It's made to tape up. It's made to tape up air conditioning vents, and it's called HIVAC tape, and you can buy it at any hardware store, or especially off the internet. Now you might say, well, shouldn't you use copper tape? It has better conductivity. Yes, it does. Copper tape has a 20 to 30 to 40% better conductivity than aluminum. But as you saw from that last table, aluminum has a thicker skin. It has a 25% thicker skin. So copper and aluminum tape are about equal for building magnetic loops. You don't gain anything for building magnetic loops out of copper tape. You can build it out of aluminum foil tape. Some people have asked me, well, you can solder to copper. Yes, you can, but I don't solder to it anyway, because if you solder a wire to it, you'll quickly pull the copper tape off. Just so I solder my wire to brass washers and tape it on with the packaging, with the ordinary packaging tape to hold it on. I don't try to solder to copper tape anyway, even if I use it. But look at the cost. Inch and a half PVC pipe. There it is on the right there. Schedule 40, inch and a half PVC, 1.9 inches in diameter. It's the same, roughly the same as 2-inch copper pipe. But in late 2022, when I did this slideshow, a 10-foot section, and you'll need two of them to build one of these loops, was $128 in copper, $16.78 in plastic, and the foil tape was a few dollars. Which one is optimized? Both of them work identically for a magnetic loop. I think you can see which of these two choices is the optimum. Does the copper work any better? Not a speckle. Okay, factor number 3 to optimize a magnetic loop if you're going to build one. Now, you won't find any commercial loops built out of PVC and foil, but if you're building one, you can certainly build one out of copper, PVC, or other plastic pipe and foil. How about the shape of the loop? I already mentioned that I think square is best, and I'll show you why. In 1968, that's when the magnetic loop came into the ham radio world. It came into the ham radio world by Lou McCoy. He's now a silent key, but he published an article in QST. I have a copy of this magazine, although you can buy copies of this magazine off the internet. And he read an article by Kenneth Patterson, who was working for the War Laboratory at the time, and developed this magnetic loop for the War Laboratory in Maryland for the war in Vietnam. They were using HF extensively in Vietnam, still do use HF in the field, and Ken Patterson's Army loop, as it was called, was 12 feet in diameter, and he made it octagonal. He made 12-foot sections of aluminum pipe, and which wasn't really big enough, by the way. And he flattened the ends and bolted it together for good conductivity. But what I'm pointing out here is this shape, this octagonal shape, got stuck in the mind of hams as an optimum shape for magnetic loops. And hams have been aping this shape ever since. I remember seeing this way back in 1968. I was living in England at the time, and I opened up the QST. I got a copy of it over there. And I said, wow, that's a great thing. I'm going to build one of those. And hams ever since, they heard the word loop and they thought round or octagonal. That's the shape. And ever since, hams have been thinking round and octagonal. But to me, it is not the optimized shape. Michael Faraday, of course, most of you will recognize the name Michael Faraday. He was a radio pioneer. He was a big fan of loops, and he studied them quite extensively. And he discovered that loop antennas do not care what the shape is. They only care what the area is. Now, on the right, you see over there a drawing that I made. All three of those shapes that I'm showing you there have the same area. There's the circle in dotted, and there's the octagon in blue, and there's a square in black. And there's a picture of magnetic loops of those three shapes on to the left there. They all have the same performance as far as a magnetic loop goes. There's no difference in the way they perform. But I ask you, which of those shapes is the easiest to build? And I don't care how you're building it, whether it's out of copper pipe with elbows or whether it's out of copper pipe and you're trying to bend it. I'm sure you understand that trying to bend copper pipe into a circle is a nightmare. I see whoever's got that one on the who made that one on the upper left had a lot of fun bending that copper pipe into a circle. I know lots of hams have decided, oh, I'll make it an octagon. I'll use those 45-degree elbows that I can buy at the hardware store. Those elbows, copper elbows, 45-degree elbows, are sinfully expensive. That loop would have cost a fortune. Even a square loop at the bottom, the elbows are, you'll still need elbows. But the square loop is the easiest loop to build. And look at how much difference it is in size. Trivial. Square loop is the optimal shape for a magnetic loop. Don't build a round loop just because it's got the name loop. A square is a loop just as much as a round circle is a loop. Don't be fooled by the name. Square is optimized. And don't do this. Don't make it a rectangle. A rectangle compromises it rather quickly. This magnetic loop is not optimized. Where is square, I think, the best in another way? Well, it's this guy looking over your back fence. This is where square really comes into its own, I think, or for homeowners association. That busybody that wanders down the street and looks over your back fence is what you got in your backyard. If she sees an octagon standing in the backyard, she says, what's that funny looking thing in your backyard? But if she sees or he sees a square back there, he's going to think it's a rose trellis, not an octagon. Nobody builds octagonal shaped rose trellises. Well, maybe somebody does. But this is where a square is an optimum shape to make a magnetic loop out of. Humanly, and you'll avoid that guy on the left if you build it out, if you build it square. Or do this to it. Now, I thought this was a very clever idea. This probably really pleased the neighbor next door. Neighbor looked over the fence and said, isn't that sweet? I think that's very nice. I like that, a heart shape. Isn't that very nice? Now, it's not, this particular loop doesn't have a big enough conductor. It violates my first rule there, but it is nice looking so that the neighbor that looked over the fence didn't think ugly, thought, oh, that's nice. I like to see that heart shape. But it did have a good tuning capacitor. That tuning capacitor there at the top, which is the two ends of the heart together, worked very well as a tuning capacitor. So this was a pretty good idea. But if you're going to make a magnetic loop that goes in your backyard, a square is a heck of a lot more attractive than an octagon or even a circle. Factor number 4, self-resonance. This is one, if you're a magnetic loop builder, you probably aren't even aware of. Probably aren't even aware of this. Most loop builders haven't ever even heard of the term. But self-resonance is important if you're a magnetic loop builder. And if you are a builder, you need to know it. It sets your maximum frequency. You may not have had the need to know this. You may have just stumbled onto it by accident if you built a loop. But here's one to learn. What is self-resonance in a magnetic loop? Well, here's just a plain loop with the gap at the top for the tuning capacitor. It is a loop like that already has some inductance to it. It's a loop of wire, A loop of wire has inductance. It's natural to any loop of wire any conductor, any conductive loop that you make, there is some natural inductance there. It's called self-inductance. It also has self-capacitance. That piece of wire on the right has capacitance to the wire on the left. The wire at the top has capacitance to the wire on the bottom. The wire on the bottom has some capacitance to the wire on the right. And each of those pieces of wire have self-capacitance to the other parts of the loop. So in any loop that you build, there's self-inductance and self-capacitance in that loop. And that self-inductance and that self-capacitance will make that loop without any capacity present across the gap have a natural self-resonant frequency. So if you take your magnetic loop, if you have one, and take the capacitor off of it and measure and put your uh, uh, meter on it, your grid dip meter or your tuning meter on it, and measure its resonant frequency, you'll find it has a dip at one frequency. That's its self-resonant frequency. And every magnetic loop will have one, even without a tuning capacitor on it. The point is, and you need to know this, your magnetic loop can't be tuned any higher than that self-resonant frequency. So if you make it too big, there'll be bands you can't tune. For example, that Maggio magnetic loop won't tune above a certain frequency, and that's one of its limitations. We'll get to that in a minute here. But a magnetic loop, if you make it too big, might not be able to tune all the ham bands. So keep this in mind. Here are the self-resonant frequencies. And by the way, don't forget, if you don't have to write any of this down. Just go to my website, w6nbc.com slash slides, and you can get all of these slides for yourself. And this chart will be in there if you want to get this chart. This shows you square loop edge dimensions in feet and the self-resonant frequencies of the square magnetic loop. Here you see a 4-foot magnetic loop, square magnetic loop, is self-resonant at 31 megahertz, which means if you just make the loop itself, put no tuning capacitor on it, it'll be self-resonant. It'll show you a dip with your antenna analyzer at 31 megahertz. As you can see there, what the arrow is pointing. And remember, a magnetic loop can't tune any higher, so a 4-foot square loop won't tune 6 meters. If you want a 6-meter loop, you'll have to make it more like about 2 feet in diameter, which you can see right here would be, if I get my arrow up here, right here would be 50 megahertz, and you can see you'd need about a 2.5-foot loop or a 2-foot loop you'd need approximately for a 6-meter magnetic loop. If I show it, it's 63 megahertz is probably what you'd want for a 6-meter loop. And if you wanted one that'll be for 20 meters, you'd need an 8-foot loop would be 15.6 megahertz. And a 40-meter loop would have to be 7.8 feet, 16 feet in diameter. Here's an interesting little loop that a friend of mine built. He built this and here's a design tip. If you build a monoband loop, make the size just above the band for minimum tuning capacity. This is a 6-meter, 2-foot self-resonant 6.3 megahertz loop built by Rob Janke, his friend of mine. Here's the Ciro Mazzioni MIDI magnetic loop. This loop can't work above 10, I should say 40 meters. 40 meters. That's a mistake on the slide. I need to correct that. It's a 6.5-foot loop. It's got big enough conductor in it, as you can see, as I pointed out, but it's limited in upper frequencies. Okay, here's takeaway for you. No one magnetic loop can work all ham bands. You might have not realized that. You might think, oh, those ads say works everything, high efficiency. No, there's no such thing. If you want high efficiency, you're going to need more than one magnetic loop. Here's an optimized example. Here's my 4-foot square magnetic loop. There it is. It's made out of 1.5-inch PVC pipe with common elbows and one T at the upper left. You can see up there, and you can see what you'll see in a minute what that's for. It's 1.9 inches outside diameter, which you saw earlier is efficient down to about 40 meters. And it's 4 foot square. The actual pipes themselves, the lengths of these pipes are 42 inches. Now you don't write me for an article on how to build this. You just order the slides, and there's enough information here to build one of these quite easily. This is just a T section piece of a 2-inch pipe. This no, actually it's a piece of inch and a half pipe, like the loop itself. And this is just a T cut off to act as a saddle to hold it up. So there's enough information here just from the picture to build this loop. It's just a standard 1.5-inch elbows cut in half, and they're held together with sheet metal screws into the pieces of PVC, which are 42 inches long. This is a T that's cut in half. I cut them in half on a bandsaw. They're lined inside with aluminum foil to make the connection through. It takes a little tricky to get the aluminum foil inside, but with a little bit of effort, you can do it. And this thing sticking in here is, which you'll see in a minute, is part of a tuning capacitor. This at the top is part of the tuning capacitor. No vacuum variables, no variable tuning capacitor. This is a cheap tuning capacitor, works slick. Here's a drawing of it, you can see, and this is more than enough to build one of these loops for yourself. These pipes are 42 inches long. Total here to here is 4 feet. Here's a piece of 2-inch pipe up the middle to support it with a T cut in half to hold it up, a bolt through here to tie it down, and so this is plenty of information. These are little 14-inch sections of 1/2-inch pipe with the ends squashed and a bolt through. This is a U-bolt that allows this to move. This makes the coupling loop. This is a little piece of PVC board mounted with an SO239 on it, coupling over to the coupling loop. And this has foil on it, except in this area, and it connects to the main loop. So this is pretty much all the information you need to build. A lot of these loops have been built just from this picture. But remember, you can get this information, W6NBC.com/slides, and you'll get all this information. The drawing is not to scale, by the way. Here's how you put the foil on, by the way. This is a little tricky, but this is just 4-inch high vac or stick-on aluminum foil tape that I got from Amazon, 4 inches wide. You can get it from Amazon for $13 or $14 for a big roll of it. And the way you put it on is you fold over a bit at the end, take off the backing, and stick a 1-inch wide piece to this piece of carpet, and then pull off the rest of the backing so that the glue side is facing up towards you. So just a little bit of a tab is stuck down to the carpet at this end, and then you pull off the rest of the backing so that the gluey side is facing you. Then you take your piece of pipe, and there it's 42 inches long piece of pipe, and then quickly go boom, and push it down onto the sticky stuff. Then you snip the ends off that are stuck to the carpet, and then just roll the pipe back and forth, and it goes right onto the piece of PVC pipe without any trouble. You have to do this twice because it takes 2 pieces of the aluminum foil tape, 4-inch aluminum tape, to go around the pipe. Piece of cake to do it, though. The elbows are a little trickier. You have to cut yourself a little L-shaped piece, but with a little bit of effort, you can get it inside of the elbow. The elbow is just cut in half on a bandsaw, or if you're careful, you can easily cut the elbow in half with an ordinary hacksaw. It's not that difficult. You can see the two screws that have come through the round pieces, the round areas there on the end is where the pipe comes in, and this area and the pipe are in contact with each other, and that surface is plenty of surface area for there to be good contact by capacitive coupling and uh, direct coupling. This surface connects to the pipe. It takes a little bit of work to get that into the elbow halves, but a little bit of work and you're just fine. Now, some people have asked me, could we use conductive paint? Yes, you can. You can use conductive paint inside of there if you want to. You could even use it on the pipes if you want to, but the stuff is expensive. It's made by M&G Chemicals. It's called shielding paint, and it comes in three different versions with carbon in it. That's not good enough, but they do have two versions that have copper nickel particles in them, or just copper silver particles in it, or nickel particles in it. Either of those would work, or you can get it in a spray can, but it's pretty expensive. I have tried it and it works fine, but I don't recommend it. I recommend just taking the extra effort to get the aluminum foil inside of the elbows. Or you can use some of this shielding fabric. Shielding fabric is interesting stuff, and it's relatively inexpensive. And this is from Amazon. It's just called conductive copper nickel plated shielding RF shielding fabric for smart meters. And you can buy it. $13 will buy you a 39-inch by 43-inch piece, or you can buy bigger pieces if you want. And this stuff is really conductive. You put an ohm meter across it, and it looks just like a piece of wire. So this is useful stuff for this purpose if you wanted to use it inside of the elbows. And I have built a magnetic loop, which I'll show you a picture of it in a minute, of a different material to take up on. I built a blow-up magnetic loop, which you'll see here in a second, for mountain toppers, which you can disassemble, put it inside of a backpack, and hike it to a mountaintop, which this guy is doing right here, which is much better than throwing a piece of wire over a rock or a tree. You can get a good radio to take to a mountaintop. You can get good portable power these days with lithium-ion batteries, and you can get a nice little laptop to do the work. But the antenna is the problem. Small whip or wire over a bush isn't so good. But here's my portable blow-up magnetic loop. This is an efficient antenna, and that all disassembles. Even the little portable stand made out of PVC pipe, it's not glued together. It's just stuck together. And that all goes in a backpack. And the loop and everything weighs about 5 pounds. Inflatable portable loop on a portable PVC stand, including the coupling loop and everything. All goes in a backpack made out of ripstop nylon and a bicycle inner tube. Okay. Factor number 5, matching. You want to do this for ruggedness and simplicity. 2 ways to match a magnetic loop. You either can do it by the double loop method, which is transformer coupling, a small loop coupling to the magnetic loop, very popular method, or you can do it by the auto transformer method, which is a tap method, where you tap the magnetic loop. That's what I prefer, this method, the tap method. I like it better, which actually is a very old-fashioned method, where the primary loop, the main loop, is tapped to make the coupling. Here's the separate loop method, which is commonly used. Just make a secondary little loop and put it opposite the gap in the loop, the other side of the loop. And here you see a typical example of it. The little secondary loop is about 1/5 the diameter of the main loop typically, and it's easy to adjust. You just squash it or stretch it out until you get a good match. It works very easily. That's the transformer method. Or, oh, by the way, this little CB, these little things that are used to make CB antennas, portable CB antennas, make excellent devices to make these coupling loops with. You use it with flattened tubing. Here's the other method. This is the tap match. As you can see, it goes at the opposite the tuning capacitor in the loop. It's the auto transformer method. It's, in fact, it goes way back to when we used to use, had these little, had vacuum tube radios, and inside the little cans were coils, and we would often tap the coils inside of the little transformer cans that you see here. These little cans had coils inside of them, were often tapped to match the impedances inside the can. And that's what this method of matching is. And that's what I like to use on this optimized magnetic loop that I'm showing you here. The shown to you already, but this shows it to you in a little more detail. There's a little plastic, a 2x4 plastic piece of plastic made out of PVC that's screwed to the main loop with one of the screws that bolts it to the main loop is also for mounting the main loop. That's this bolt right here that goes through this little PVC plate. This is just a sheet metal screw. The plate has got aluminum foil on part of it. That's this part right here, which attaches that plate to the connects that plate to the bottom pipe. It has an SO239 connector on it here, the center of which is hooked over here to this three-section movable arm, which is made of 14-inch long, half-inch pieces of aluminum tubing squashed at the end and bolts put through the end with wing nuts on it. Goes over here to another little bar and a U-bolt, which is used to make this loop in here, which is the tapping loop, which is actually a coupling loop, which moves up and down this pipe, or it can be brought down onto this pipe if you want to. This is a variable coupling loop, or it's a variable tap. You can find the 50 ohm point. When you think about it, up here is the high impedance point of the loop. Down here is the low impedance point of the loop. Somewhere between here, which is very low impedance, and somewhere up here, which is very high impedance, is going to be a 50 ohm point somewhere along this pathway. Going to be several thousand ohms up here, almost 0 ohms down here. Somewhere along here is 50 ohms. And all you got to do is move this point here until you find 50 ohms, and you get a perfect match. It adjusts very easily. More recently, I've discovered that the best way to do this is to let this first element lie straight and these second two hump up here. But you'll find that adjustment quite easily just by moving these around until your antenna analyzer hooked onto this SO239 connector reads 1-to-1. It's easy adjustment. Factor number 6, tuning. This is still developing, by the way, and this whole design is still developing. You can use a vacuum variable on this design if you want to spend the money, though getting vacuum variables, what with the troubles over in Russia, most of the vacuum variables come out of Russia. They're hard to get these days, and they're terribly expensive. Anyway, why bother? And rotary capacitors have their difficulties, and they're pretty expensive. They have difficulties in the connections that are made. They have losses in the wipers on them. I don't recommend them, but though you can use them. Here's one of my readers who used a rotary capacitor on one of my loops. Here's one of my loops down here, and he decided to use a rotary capacitor for remote tuning. Okay, here's my tuning capacitor. This is really cheap, but it works very, very well. It's called an internal linear tuning capacitor, and you can only do this with a square loop. Here's how it works. Inside of the top bar is another piece of PVC pipe, also covered with aluminum foil. And it's pulled back and forth. If I move back, one slide here, you can see it's pulled back and forth with just a piece of parachute cord. You can pull it back and forth. The parachute cord goes out both sides to pull this little piece of pipe, which is a piece of 1-inch PVC pipe covered with aluminum foil. If this aluminum foil straddles this gap up here equally, you've got two capacitors in series, one capacitor here to here and one capacitor here to here, and they're connected in series down the middle. So you got this little double capacitor here straddling the gap. If you move it off center by pulling it off center with the cords, this capacitor gets smaller and this capacitor gets bigger. And if you know capacitor theory, the smaller capacitor of two capacitors in series always dominates. Therefore, as you move it off center, the capacity diminishes. And so this is a very easy tuning capacitor to tune this whole assembly. But you make it fairly small. I use for fine tuning. Band tuning is done by simply taking a piece of 2-inch PVC pipe, cutting it in half, and putting some aluminum foil on it too, as you can see up here. And these are pretty easy to figure out. You just cut yourself a piece of pipe and experiment with it. Put a piece of aluminum foil on it and set it on top of the top of the loop. And it too works the same way by sliding it back and forth. On center, it has the maximum capacity. Off center, it has the minimum capacity. And its length is half the length from here to here. That's how long it is. And this is just a little bit shorter on the ends. You'll easily work out how much aluminum to put on that tape for the various bands. And you make one of these for each band that you want to work. These are the band tuning capacitors. And they move the loop much farther. You don't use these for tuning, for fine tuning. Use these for band tuning. You work these out so you'll have a 20-meter version of this, a 40-meter version of this, an 80-meter version of this, and so forth. And you just set that on top, and then you use the little pull cord one to do the fine tuning with. Piece of cake. Put your antenna analyzer on it, slide these around, put the band tuning on, slide the little one until you get a dip, and you're fine. You're way to go. Just step outside and do that quickly, and that's all you need. I've even had some people who've motorized this, who've taken these cords, taken them down to the bottom, put a little stepper motor at the bottom, and motorized this fine tuner. And here example is one shows you a picture of the slider that slides in. There's a 1-inch piece of PVC, comes in through the T at one end. You can put marks on that pipe for the various bands, and that's the 20-meter one at the top. And you just say you make up one of these band tuners for each band. Here's the T at the end, at one end, and the mark there at the end tells you when I've marked it. That's when the thing is on center. That's the maximum capacity. And if I were to pull it out, you'd see I have it marked for the minimum capacity as well. I can't use a sheet metal screw for that particular one. So there's a stainless steel clamp around this one particular one. The rest of them have sheet metal screws at that point, because I couldn't put a sheet metal screw in through there. The slider wouldn't work. Now, there's one little problem showed up though. One little tiny problem showed up, which I've yet to completely resolve. So I'm interested in some any feedback that you have. This loop, as I've shown, will work fine for 100 watts of power. Above 100 watts of power, PVC is not a really good RF plastic. It will get warm. And in fact, if you put more than 100 watts of power into it, this loop will start melting because PVC will get hot. Its dissipation factor isn't very good. I show you this because this is another loop. This is another loop where my good friend Rob Jansky used a nylon screw inside of a 3D printed capacitor, a tuning capacitor they used. And as soon as he put more than 50 watts on it, the nylon screw melted and squirted out a jet of nylon plastic. Well, PVC is not quite as bad as nylon. Nylon is an extremely bad plastic to use in an RF environment. Hams think, well, not all plastics are the same. They're insulators, aren't they? Yeah, but not to RF. RF doesn't treat all plastics the same. I do a whole talk on plastics, by the way, if you're interested. In fact, here's a chart showing you the various plastics and whoops, showing you the various plastics and which one is good for various reasons. I won't dwell on that, but it's in the it's in this presentation if you want to look at it in some greater detail later. So I've been trying to figure out how to replace that top pipe with instead of using PVC to replace it, for example, with PEX pipe, which is polyethylene. Polyethylene is a good RF plastic that would allow the power of this 4-foot magnetic loop to be taken up to full legal limit. Unfortunately, PEX doesn't come in the same sizes as PVC. For the rest of the loop, you can make it out of PVC because the RF is not subjected to the PVC on the inside of the aluminum foil. But if you're making the capacitor at the top, as I'm showing, you are limited to 100 watts for this loop. The outside capacitor I will make out of PVC bottles instead of PVC plastic. But so that's why this capacitor is still somewhat in development. Okay, factor number seven, and finally, receive-only loops. Here's a point that I got from the IEEE, the Electrical Engineers Institute. If you're going to use a magnetic loop as a receive-only antenna, and a lot of people do, the IEEE did a study of this, and they discovered that it's better if you're going to use a loop as a receive-only antenna, not to match it, not to get it to have a one-to-one SWR, but in fact to feed it into your receiver high impedance, and just to take it straight across the gap in the loop, high impedance. It won't be 50 ohms across the gap. Don't use a matching coil or a matching tap, but just feed it directly across the gap and take it into your receiver high impedance. It will have better bandwidth and better signal to noise if you're making a magnetic loop as a receive only antenna. Just connect your high impedance coax directly across the gap where you would normally put the tuning capacitor, and take that directly into your receiver and connect it high impedance into your receiver, and you'll get better bandwidth and better signal to noise on your receiving magnetic loop into your receiver. If you're using a magnetic loop, let's say as a noise canceling antenna or something like that, or just for receive only, don't match a receiving magnetic loop if that's all you're using it for. That's just a little piece. You can if you want to. The difference won't be a lot, but a magnetic loop for receive only is best used unmatched. Okay, here are some final takeaways on magnetic loops. I haven't finished this yet, and I intend to do this. I am planning to expand this 4-foot square loop into a 2-turn magnetic loop, or even a 3-turn magnetic loop. The reason is this. If you look at the equations of a magnetic loop, and they're readily available on the internet, by the way, you can just search for the equations of a magnetic loop. The equations of the magnetic loop specify that the efficiency of a magnetic loop goes up as the square of the number of turns. So a 2-turn magnetic loop is 4 times as efficient as a 1-turn magnetic loop. Not twice as efficient, but 4 times as efficient. A 3-turn magnetic loop is 9 times as efficient. So the losses in a magnetic loop, which is its biggest enemy, is 9 times as great. This means you could use fairly fine wire in a 3-turn magnetic loop and have it be as efficient as a 1-turn magnetic loop that you feel like you have to build out a 2-inch diameter conductor. So there's some advantage to making a 3-turn magnetic loop out of fairly small conductor. So this is well worth exploring, and I'm going to do this, but I just haven't done it yet. Here's another thing you see on the internet sometimes. People who'll decide, well, I'll make a magnetic loop out of flat strap. And here's one builder. This is just something I got off the internet, who decided he'd use a screen and make a really wide flat strap. That'd make a real good magnetic loop. Wrong. He ignored something. Skin effect says that the current in any conductor will seek out the points in any conductor that's farthest away from the middle. So what does the current do in this conductor? It immediately rushes to the edges. There's no current down the middle of this. All you've got here is 2 conductors separated by a great distance. This is not an efficient way to do anything. It seeks the edge. This is a very inefficient mag loop. Some people have thought, oh, I'll do this. I'll make the loop convoluted. This suffers from the same thing. That flat strap and skin effect eats this loop alive. Don't think that you can make a magnetic loop this way. This is a very bad magnetic loop. Some people have thought, oh, well, I'll get some copper tape. He hadn't learned the lesson about aluminum tape, but so he used copper tape, and I'll make it a helix. I'll make a helical magnetic loop. Again, edge effect eats this one alive. This too is a bad magnetic loop. Don't do this. Some people have thought, oh, I'll make a slinky magnetic loop. Same thing. Small conductor, very low efficiency, very high loss loop. Slinky magnetic loop doesn't work well. Also, don't do this. Don't make a horizontal mag loop. Mag loops are only good as verticals. They have very bad radiation patterns as horizontal loops. Their radiation patterns only are good in a vertical situation. I know a lot of hams have tried them as horizontals, but haven't got good results out of it for the very same reason. The radiation pattern stinks. So, closing thoughts. Here's a closing thought that's important to remember. There is very little benefit to putting your magnetic loop up high. Don't think, oh, I'll put my magnetic loop up on my rooftop. Don't do it. Don't bother. It'll work fine up on your rooftop, but magnetic loops work very well ground mounted. They work almost as well sitting right on the ground as they do up on your roof. So don't bother to raise them up very much. It doesn't help very much at all. So here are the 7 points again. You need to learn them if you're going to get into magnetic loops. Big conductors compared to the size of the loop. Construction material, don't bother with heavy metal. It's a waste of money, a waste of weight, difficult to build. Loop shape, square. No no advantage whatsoever. Just because it's called a loop doesn't mean it's got to be round. And it's expensive to build them some other shape. And you can't use the sliding capacitor if you build it anything but square. Self-resonance, remember that limits your maximum frequency. Matching method, well, matching method, the best matching method is the tapping method. Or at least the separate loop. And the tuning method, I think the sliding capacitor and the sliding and the loop on and the half and the half loop thing on top is the best way to do it. It's the cheap way to make it. Don't bother with heavy, expensive tuning capacitors or with vacuum variables. Of course they work, but you can motorize the simple method too. And for a receive-only loop, just match it straight across the gap. Don't match it to one-to-one. You don't need one-to-one match when you're matching a receiving loop. Just match it straight across the gap and take it high impedance into your receiver. So if you build one of these loops and you optimize it my way, send me photos. And if you've got other ideas, particularly on how to motorize it or on how to do it other ways, and I've gotten lots of responses to this, send them to me, particularly with pictures. I love it. And that's it, folks. This is my little doggy Lolly. No, she doesn't have a German call sign. She's not D0GGY. That's my email over there. You can contact me anytime. My website's W6NBC.com. And again, you can get the slides with all those informations on it. W6NBC.com/slides. That's all, folks.
Cool. Thank you, John. Right. Are there any questions for John? Noah, here. Use the microphone over here.
So you said that height doesn't necessarily matter, but have you measured inside?
I'm not hearing you very well. Can you get any closer?
Do I sound better now? Testing. 1, 2, 3.
A little bit. There's so much room echo from where you're talking.
Yeah, there's a lot of room echo. I can repeat, or do you want to come up here and?
Yeah, I'll come up.
Okay. Let me turn the video on. This room is always a little bit fussy on us.
Where's the? There.
Just right here.
Yeah. So you were saying that you can keep it close to the ground, but let's say that you wanted to have one in like an apartment or something like that. How much of a difference have you guys measured versus inside versus outside?
Well, they work fine inside. I'm not saying that you have to have it close to the ground, but don't be afraid to keep it close to the ground. That's all. You can mount it high if you want to.
Oh, no. What I was asking is if inside matters really compared to outside, like in a city environment.
Inside matters, of course, as it does for any antenna. So I don't think being inside is much different than any other antenna that's small enough to work inside. I mean, well, it just depends on what the house is made out of.
Well, yes, that, and also that it's much narrower, right? So it's less vulnerable to RFI.
Yeah.
Okay, thank you very much.
Cool, thank you. Any more questions? All right, thank you again, John. We're going to go ahead and take a quick 5. Oh.
Okay, well, thanks for having me. Have me back anytime. I'm always happy to give these presentations, and I'll say 73 to you.